AI models are great at understanding intent, assist users, and make decisions. But there's a fundamental gap. They can't natively pull real time data or execute actions in your systems. This creates bottleneck that forces developers to build extra middleware, stitch complex API layers, and manual integrations, making AI features slower and harder to maintain. Tool calling addresses this by giving LLMs a structured way to trigger external functions and APIs. The model decides what happens next, and your infrastructure carries out actions deterministically. Hello everyone, I'm Sanskriti Harmuk, Developer Relations at Vultr, and in today's Tech Talk, we will break down how tool calling works, why it unlocks a new class of AI powered applications, and how Vultr Serverless Inference makes it easy to execute these actions reliably at scale. After that, we'll jump into a live demo where we'll wire up a model, define tools, and watch it perform real time actions. So, without any further ado, let's get started. Vultr Serverless Inference is a fully managed environment for running large language models without provisioning or maintaining any infrastructure. Instead of deploying GPUs, configuring runtimes, or handling scaling logic, you simply make a request to an API endpoint and the platform allocates the right compute on demand. Behind the scenes, Vultr automatically handles model hosting, resource isolation, and workload placement, ensuring every request run on optimized hardware designed specifically for high performance inference workloads. And because the platform uses elastic GPU auto scaling and pre initialized model containers, requests avoid cold start delays and scale seamlessly under varying load. With Vultr Serverless Inference, you can use a structured prompting, multi turn chat, and retrieval augmented generation features all within the same interface. Now, let's talk about tool calling. Tool calling is the mechanism that allows large language models to invoke external functions when a task requires actions beyond text prediction. Instead of embedding logic directly inside the model, you expose functions to the model in the form of tools, each described with a name, purpose, and a structured JSON schema that defines its input parameters. This allows the model to understand what operations are available, what arguments are expected, and when a function is the correct way to fulfill a user's request. When the model determines that a tool is needed, it emits a JSON based function call containing the tool name and arguments. Your application executes that function externally and returns the result back to the model. The model then incorporates that result into a grounded and contextually accurate final response. This enables deterministic, verifiable actions that cannot be performed through text generation alone. Let's dig in further. When tool calling runs on a Vultr serverless inference, the entire workflow becomes an orchestrated request response pipeline between the model, your application, and Vultr's inference runtime. The process begins when a user prompt is sent to a serverless inference endpoint that includes tool call definitions. Then, the model analyzes the input, determines whether a function is required, and emits a structured tool call in the response. Rather than performing the action itself, it delegates that execution outward through this tool call, allowing your application to interact with real APIs, databases, or custom logics. Once the function executes, your application returns the tool result back to the model, using the required role tool message tied to the original tool call ID. The model uses that function to generate a grounded final answer that blends natural language reasoning with real world data from the executed function. Vultr serverless inference ensures this loop remains fast and consistent by handling the inference layer, scaling the GPU capacity, and keeping the containers available throughout the interaction. Now that we understand how tool calling works and how Vultr serverless inference orchestrates execution flow behind the scenes, let's see the full life cycle in action. In this demo, we'll walk through a real tool call request, from sending a prompt to the model triggering a function to executing external logic and generating a grounded LLM response. This will show how the entire workflow behaves in a live environment using Vultr Serverless Inference. Before we begin exploring tool calling, we first need to provision a Vultr Serverless Inference subscription. For that, open the Vultr Customer Portal, locate Products menu on the left sidebar, and choose Serverless Inference. Here, click on Add Serverless Inference and provide a label to your subscription. Below that, you'll find a list of supported models, including Kimi K2 Instruct, which we will use today because it supports function calling. Review the pricing details and acknowledge it. Once done, click on Add Serverless Inference. When the inference subscription status changes to active, click on it to expand. Here in the overview page, you'll find an API key. This key authenticates all requests sent to Vultr Serverless Inference endpoints. Copy it and store it somewhere secure. Through this management page, you can also monitor token usage and overall cost, and leverage features like prompt to quickly test models' response. Use multi-turn chat to design interactive flows, or generate audio-based output using text-to-speech. You can even upload and index documents for RAG-based applications with Vultr Serverless Inference. Now for extended capabilities, let's switch to the API reference page. This documentation can be accessed at api.vultrinference.com. It lists all the available REST endpoints with their request structures, response schemas, authentication requirements, and the supported models. Now here within the chat completion endpoint, you'll notice a tools parameter. This parameter defines the functions that the model is allowed to invoke. When included in the request, it enables full function calling behavior, allowing the model to determine when a function call is required, emit a tool call object containing function name and arguments, and wait for the external function result before generating the final response. Now, instead of executing individual curl commands and manually simulating tool calling workflow, let's use a practical Python script that shows how to build a real-world AI agent that fetches live weather data by combining Vultr Serverless Inference with external APIs. Let's switch to our workstation to see it all in action. We'll start by grabbing the Python script from the Vultr's code samples repository. The curl command here fetches the file and saves it in our current directory. Before we run it, let's understand what this script actually does. The script starts with the standard Python imports: OS for accessing environment variables, JSON for passing and serializing data, request for making HTTP calls to APIs, and .env for loading API keys from the environment. Next, we configure the API connection by defining chat completion endpoint and loading the API key from environment variables. The script then performs a validation check to ensure the API key is present before execution. After that, it constructs the required HTTP headers, including the authorization header with the bearer token along with the standard JSON content headers. Then this helper function converts city name into geographic coordinates by querying geocoding service nominatim powered by OpenStreetMap. It accepts a city name such as Tokyo and returns the corresponding longitude and latitude values. If no matching location is found, it safely returns none. This step is essential because the weather API requires precise coordinates rather than city names. Now this function serves as the actual tool capability exposed to the AI model. It begins the input validation by retrieving the coordinates through the helper function. Using those coordinates, it queries the OpenMeteor Weather API to obtain real-time weather conditions. The function then extracts the relevant fields, including temperature, wind speed, wind direction, and timestamp, and finally returns them as a structured JSON object. And this is where the magic happens. We are making our first request to the Vultr Serverless Inference. Here we are using Kimi K2 Instruct model. This model is designed and optimized for agentic workflows. Unlike many models that have tool calling bolted as an afterthought, Kimi K2 was architected from the ground up with function calling as a core capability. In the request payload, we have messages array that carries the conversation history. For example, at the moment we have user's natural language query. On the other hand, the tools array is where we declare functions that the model is allowed to call. Each tool definition specifies the type function to indicate that it is an executable function, followed by a function name, a descriptive description that guides the model on when to invoke it, and a parameters block that uses JSON schema to define the expected input structure. The required city field ensures that the city parameter must be provided for the function to run. And here the tool choice is set to auto to let the model autonomously determine whether a tool invocation is necessary. Now we process the model's response. If the model decides to call a tool, the response contains tool calls array. Here we extract the function name, the arguments the model extracted from the user's message, and a tool call ID, which is a unique identifier linking the request to the response. We then actually execute the function and get the real-time weather data. Finally, we make a follow-up request to the Vultr Serverless Inference, but this time we are including the complete conversation history. The original user question, the model's tool call request, that is its decision to call get weather, and the tool result implying the actual weather data we fetched. The model now receives the real-time weather data and synthesizes it into a natural conversational response for the user. Lastly, the main function orchestrates the entire workflow. Now that we are aware about the execution flow, let's set up our environment by installing Python's virtual environment support. To keep our project dependencies separate from the system-wide Python packages, let's create a new virtual environment in a folder called env and activate that environment. You'll now notice your terminal prompt changes to env. That means you're now working inside the virtual environment. Next, we install the required lightweight dependencies for our application. This includes request to make HTTP calls to Vultr Serverless Inference API and weather services, and python.env for secure API key management. Now we need to set our Vultr Serverless Inference API key as an environment variable. You can fetch the value directly from the overview page of your inference subscription. Finally, let's run the script. When prompted, input the city name and hit enter. Now that the execution has completed, let's see what happened behind the scenes. The script first sent the user's query to the Vultr Serverless Inference along with the tool definition. The model evaluated the prompt, for example, what's the weather like in Delhi, and determined that answering it required external real-time data. It then generated a tool call requesting the execution of get weather with the argument city is equals to Delhi. With the tool output available, the model generates the final natural language response. Instead of returning a raw JSON, it interpreted the data and synthesized it into clear, readable explanation of the current weather conditions. In this way, you can replicate a similar pattern in your application to integrate tool calling, automate data-driven operations, or build agents that interact with real-world external systems. If you would like to explore the approach in more detail or review the equivalent curl examples, then refer to the supporting reference guide linked in the description. To summarize, combining tool calling with Vultr Serverless Inference gives you a unified, fully managed environment for running LLMs that can interact with real-world systems through deterministic function execution. If you're ready to experiment with this yourself, then try deploying your first inference workflow using Vultr's API endpoints and explore tool calling with your own functions. To get started, claim $250 in free credits on a new Vultr account using the promo link attached in the description below. For any questions, guidance, or to learn from others building AI-driven applications on Vultr, join the conversation in the Vultr community forum. Thank you so much for joining us today. We hope this tech talk helped you build faster, more reliable, and more capable AI workflows using Vultr Serverless Inference.